Welcome back to Seacoast High School's remote trigonometry class. My name's Eric Fearing. I use he, him pronouns, and most of my students just call me Mr. In this video, we're working on Competency 2's Benchmark 4, which is about using the laws of sines and cosines in context. I'm going to show you two types of problems today. One of them really barely has any context at all, but we spent a lot of time doing specific problems for benchmark 3 about solving triangles. So we're going to start with this multi-step version of solving triangles today. So here we have an obtuse triangle with a 105-degree angle at C and two known sides that surround that angle in the side angle side pattern you might know from geometry class. This is perfect for the law of cosines like I talked about in the last video. If we knew two different sides, we would want to start with the law of sines to prevent getting an unclear quadratic we had to solve and remembering far more algebra than we need to carry a bunch of decimals through. So here we're ready to use the law of cosines. I want to label the sides with the points that we have on the angles. 22 would be A, 27 would be B, and we are missing side C. The law of cosines you can always look up for yourself. C squared equals A squared plus B squared. That's Pythagorean theorem. And we make it the law of cosines by subtracting 2AB cosine of C. One angle, all three sides involved. We're going to solve for C squared first. So that remains our variable. A is 22. B is 27, minus 2 times 22 times 27, cosine of 105 degrees. Barely fits on the paper, but it will be just fine on our calculator, which we need to pull up. So we're going to key this whole thing in. 22 squared plus 27 squared minus 2 times 22 times 27 times the cosine of 105 degrees gives us 1,520. C squared equals 1,520. Don't put 1,520 in for the length of C. It makes no sense. It's not 1,500 feet compared to 27 feet and 22 feet. We do need to take the square root of both sides and find that C is approximately, its square root, that last answer we got, 38.99. That's a solid 39 feet right there. So I'm going to label my triangle 39 feet. When you go to put this into the Google form, if you choose to do that instead of take a photo and upload, you're going to want to make sure that you're answering the right part to the right prompt. So you're going to have one that says to enter angle A, one to enter angle B, and one to enter side C. Make sure you're doing the one that says side C, or whatever letter it happens to be on the problem set. Once we know all three sides and this angle, we can start to use the law of sines to find a different side. So B, the angle over on the bottom right, is related to this side. That's 27. A, the angle on top, obviously related to side A, 22. We know the pair of 39 and 105 degrees, so I'm going to set up my proportion. Using the pair of C and C. The sine of 105 degrees over 39 feet is going to be equal to the sine of, you can pick either one. I'm going to go with A. Sine of unknown angle A over 22 feet. So we've got two pairs. This will give us A. You could set it up for B instead. Once you get one, you could do the law of sines again to get the other, but it's a lot faster to use the triangle angle sum property. So by the time we're done solving this triangle, we'll have done the law of cosines once, the law of sines once, and then applied the triangle angle property so that we just subtract from 180 for the missing angle. To solve this proportion, we multiply by the denominator with the variable, and then we're going to, that'll give us the sine of A. Let me do that on the calculator actually. Figuring out what we had before. I've got 22 times the sine of that 105 degree angle divided by 39 feet. Gives us a value of approximately 0.5449. That's the sine of angle A. We want angle A itself. That means we're going to do the inverse sine of that answer. And writing it out is not something I would do if I were working on this on my own, because I'm going to let the calculator carry forward all of those decimal places. Let's hit enter to let that scroll up. Function inverse sine, back to main, the inverse sine of that answer gives us 33.01, call it 33, approximately 33 degrees. We can label that on our triangle. So now we know C is 39 feet, A is 33 degrees, and we need to know B, 105 plus 33 is 138. To make 180, I would need another 42 degrees. So 42 degrees must be B. These problems really do fill up the paper, but you can always take extra paper. It's one use of the law of cosines to find the third side in this case. If you knew all the sides, you'd use the law of cosines to find a missing angle. And then once you have a side angle pair and one more piece of information, you can use the law of sines to find the other. And then just make sure you've got all three angles that add up to 180. You'll save yourself a lot of time. If we'd used a proportion with sine of B here, we'd have found 42 degrees in our answer, and we would have been missing 33 degrees up at the top. Now, a proper problem done in context is one that actually talks about a story in words. So the law of sines is part of doing triangulation. If you know the direction from two different locations, and you know the distance apart those two locations are, you can find the spot and how far away it is from those two locations. So in this problem, there are two fire towers, and they're a known distance apart, and they can see smoke somewhere off in a direction from presumably the same fire, and we can use triangulation to figure out where that fire is. Which one of these is closer, we can just do from knowing the angles, but how far away it'll be is something we can solve with trigonometry. So two fire towers, A and B, are located 10 miles apart. Rangers at Tower A spot a fire at 42 degrees, and rangers at Fire Tower B spot the same fire at 64 degrees. How far from Tower A is the fire to the nearest tenth of a mile? So we've got points A and B 10 miles apart, and we have an angle at A of 42 degrees, an angle at B of 64 degrees. So A, 10 miles, B. Draw yourself a schematic. 41 degrees is our angle at A. So they're looking out that direction and see a fire somewhere along that line. Angle B, they saw a fire at 64 degrees. That's measured from where they know Watchtower A is. So something like that. Where they see the smoke must be right there. So now we're asked to find how far away that is from, I believe it was Watchtower A. Yep, Watchtower A. So we want to know this distance that we would usually call little b. So this is a law of sines problem, like I said, because we know a lot about the angles and we only know one side. The law of cosines uses all three sides. We need to know at least two of them. So this is a sines problem. We need to link the 10 up with the angle over here, because that's how we're going to write our proportion with the sine of that red angle over 10 equal to the sine of angle B, 64 degrees, over B. I'm not going to bother putting a variable here because of the triangle angle sum property. 64 plus 41 is 105. That means this is a 75-degree angle to make 180 degrees. So now we have to get our proportion solved. I like to flip both fractions. The reciprocal 10 over the sine of 75 degrees is going to equal the reciprocal b over the sine of 64 degrees. And then we're going to multiply both sides by the denominator with the variable. Multiply everything by the sine of 64 degrees. And then we go to our calculator to find b is 10 times the sine of 64 over the sine of 75. B will approximately equal, back to Desmos, 10 times the sine of 64. Okay, hit enter by accident, that's okay, we can divide that answer by the sine of 75, and we get 9.3 miles. And there you have it. That's two types of problems that apply the laws of sines and cosines. One of them, a multi-step solve a triangle, and the other one, a triangulation, to use the law of sines from two angles a known distance apart.